When we find areas, when we estimate areas under curves by adding up areas of rectangles, that's called a Riemann sum. The distance across each rectangle, the width of the rectangle, is called the subinterval. And the total horizontal distance covered by all of your rectangles is called the partition. We could, if we wanted to improve our estimate, we could think about whether we wanted to switch from LRAM to RRAM to MRAM, or maybe even use trapezoids. But if we really, really, really wanted to be certain that we were going to improve our estimate, we should add more rectangles or more trapezoids. And we would want to do that in a way that doesn't just leave one big rectangle and make all the other ones smaller to make infinitely many rectangles. We want to make all the rectangles smaller so that as we go toward having infinitely many rectangles. So we need more rectangles, and we need to not accidentally leave any big ones. We want all the rectangles to get smaller. So what if we did that? Quickly, before we see the next slide, remember that for every rectangle, we found its area by multiplying its width times its height. We could choose this height, or this height, or this height, depending whether it was LRAM, RRAM, MRAM. We could even mix and match. Use the top right corners of some rectangles and the midpoints of some other rectangles and the left corners of other rectangles, although that would make it harder to notice patterns. But it doesn't actually matter which height of the rectangle, which height of your function you use for your rectangle height. It's still called a Riemann sum, and we're still going to add up all the areas of the rectangles to estimate the area under the curve. So remember, it's a function value. It's some output of the curve, some y value of the curve that you would choose to make the height of your rectangle. It means you're going to take some x values, somewhere between 0 and 1. You're going to choose one of those x values. You might choose 0, and then you'd pick that height. You might have chosen 1, you'd pick that height. You might choose 0.5, and you'd pick that height. You could choose 0.00001, and you would choose this height. It doesn't actually matter how far along the interval you choose the x-axis. You're going to pick the y value that goes with it to give a height of the rectangle. So watch this. What if we wanted to use infinitely many rectangles? To figure out how wide every rectangle is, assume for now you want to use same size rectangles all the way along. You take the total partition and divide by the number of rectangles you want to use. So that's how we get b minus a is the width of the partition. Divide by n, the number of rectangles you want to use, and that's going to give you delta x, a change in x. That's the width of the subinterval, that's the width of every rectangle. If we use delta x to mean that, the distance across each rectangle, then you could, if you remembered some notations you used in pre-calculus, don't let this freak you out, we're going to move on from it really quickly, you could write this. Cover this up for a second. If n is the number of rectangles you want to use, you're going to count through from the first rectangle to the second rectangle, the third rectangle, the fourth rectangle, the fifth rectangle, all the way up to the nth rectangle. And for every rectangle, you're going to multiply the width of the rectangle by, this is just a fancy way to say pick some height for that rectangle. Doesn't matter if you pick C so that it's the left corner, or the right corner, or the midpoint, or some other, even a random point. You're going to take some number on the subinterval and use it as the input to your function so you can pick a height for your rectangle. So this is height times width, and the big E means just add up all those answers. So just the same way that you wrote big, long, something times something plus something times something plus something times something plus on that yellow sheet of practice papers, this is a fancy notation that says the same thing. Okay, so mathematicians, the inventors of calculus, they wanted so much to find areas under curves that they actually made this notation so they could say the area under the F curve using so many rectangles. But they decided that this notation was kind of hard to use, difficult to read, and so Leibniz, who's one of the founders of calculus, one of the creators of calculus, invented a new notation to say the same thing. So I'm going to just highlight this one more time. We're going to add up a bunch of, that's what this symbol means, add up a bunch of products. A product of a height times a width. And we're going to make the widths of the rectangle smaller and smaller and smaller so that we eventually have infinitely many rectangles. Watch what Leibniz wrote to mean the same thing, but just in like a easier to read notation. Move me out of the way here. All right, so here's the original. That's called, that big, looks like a letter E, that's the Greek letter sigma, so we call that sigma notation. This notation here in this yellow box, this is in the notation we use for a definite integral. If I want to find the area under the curve f of x between these two x coordinates, a and b, and this is a notation that it's supposed to remind us of where this notation came from. It came from multiplying the height of a rectangle times a very small, getting smaller and smaller width of the rectangle. So this dx, it's called a differential. It means a small change in x. In fact, a change in x that's so small, it's essentially zero. So width times height. And see how the sigma sort of morphed into this big letter S that means add up a bunch of, so take a sum. All right, so let's just notice the anatomy of a definite integral. This is the integral symbol that tells you you're trying to find the area under a curve. This is called the integrand. It's the name of, or a function rule for the curve that you're trying to find the area of. This is the lower limit of integration, the upper limit of integration. Those are like the smallest x and the highest x that you wanted to find the area under the curve in between. And this guy, this is what throws a lot of people off, but it really just comes from, its origin is that small change in the x, so the width of the rectangle, so that this looks like height times width. So this reminds us that this whole expression came from multiplying the height times the width. If you want to check your units, you have to remember that this represents an area, so you would multiply units from your f function, so units of the output times units of the input, because even if your change in x is very, very, very tiny, it still has units. So like some of the problems we've been doing, if this is velocity, we're finding the area under a velocity curve to find distance traveled, we'd have, for example, meters per second times seconds to give an answer in meters. And just notice this. So this little box says that x is called a dummy variable, because the result of your computation, we're going to learn how to compute integrals like this, the result does not depend on what variable you use. But that's different from saying it can be any random letter. Very specifically, if this is a function of x, then this must be the letter x. You could do the same problem and make that a function of t, in which case this would be dt. But for what we call single variable calculus, which covers all the way up through calculus BC, this variable and this variable have to match or something has gone very wrong. So I want you to think about that instead of thinking that that it doesn't matter what letter you choose. It should be the same as the input to the integrand. So if this is a function f of x, then this needs to be a very small change in x. So here we go. We have a brand new notation for finding areas under a curve. But we still haven't found out any new information about how to compute that area. So let's just practice using this notation in the context to find areas that we already knew how to find, because they trace out a shape that we know from geometry. So if we take a look at this example at the bottom of your first page of your notes, this is very similar to a problem we did in 5.1. In fact, it's the problem that the video cut out on. So I replaced that video. Make sure you see it. That video, I said, hey, if the velocity of some particle is v of t is square root of 16 minus t squared, how far does the particle travel between times 0 and 4? And you knew how to make this graph. We said this was going to be the graph of a circle, the upper half of a circle, with radius 4, and you used a geometry formula to find that area. This is a very similar question, but I haven't said anything about velocity. In fact, I don't even have a context here. I just have this new symbol, which now I know means find the area under this curve between these two x values. So that's not so bad. I'm going to make a graph of my f of x function. The square root of 4 minus x squared is the top half of a circle whose radius is 2. I'm going to draw a sketch. This is x. This is y. This is -2 and +2. This would be 0, 2. And now I know, I'm practicing, this is your first time, so don't worry if you didn't know right away, but this is a notation that means find the area between that curve and the x-axis between -2 and 2. So I'm going to color in what they're talking about. So specifically, that notation means find the area between the x-axis and the curve, which in this case is a semicircle, between -2 and +2. So I can tell now that that's a semicircle, so 1/2 pi r squared. The radius of this circle is 2. So my final answer, 1/2 times pi times 4, 2 pi. Here, since there's no context, it's not clear to me what my units should be. I'm not expected to put units on this answer, but we will have problems coming up really soon where we write an integral to match a context. And we'll have to be able to give units with our answer. Notice the units would be whatever the y units are times whatever the x units are.